Doesn't seem that there's so much for the theory, but remember that finding the double integral involves a bit of work. Involves a bit of work. Okay. Any of these? So I remember that we did from exercise 1, we did B and C. And then we did from exercise 3, number 2038, I think.
No.
Yes. We did integrate it.
Yeah.
I do believe that we integrated it.
Yeah, we did.
Yes. So now, the thing is, yes, we didn't sketch that region. We didn't sketch that region. We simply evaluated the integral. We did not sketch the region. So perhaps, just to finish with 2038, x equals y squared. X equals y squared. That's this one. X is 0. Y is 2. Y is 0. Okay. And we have to do integrate by x. So that would be parallel to the x-axis from x value 0 to x value y squared. So going like this. So this was actually the region of integration that we covered in 2038. Although we were not required to set up anything, all we had to do is find the value of that integral and sketch the region. So when we take into account everything, all the boundaries, so y2, y0, so the boundaries for y are 0 and 2, and the boundaries for x are 0 and the curve y squared. So we see that the region of integration is this one. It's not below this curve, but it's that region. What else could we do? Or should we move on to the new material? Polar coordinates today. Yes? But again, I don't want to do absolutely all these exercises, but alright. Let's see. In number 2, not all of those. I think in number 2 we could do the second, B. B. D, okay, B and D. 2B from me, 2D for you. Okay, so we have this double integral, x plus xy minus x squared minus y squared dx dy. And the region of integration is defined by x between 0 and 1, y between 0 and 2. So this means it will simply be a rectangle. If you look at 2b at the region of integration given in the task, I'm not rewriting it, we see that it's a rectangle.
Is it any paper or the
x is between 0 and 1. 0, 1. X between 0 and 1. And y between 0 and 2. So this is the region of integration, a very simple one. So for both integrals in the iterated integral, all the boundaries are going to be constant. So we don't have to worry about putting one variable into the other and dealing with curves and rewriting functions and so on and so on. So, okay, which integral will come first? Whichever.
Yeah, whichever.
Okay, whichever. So let's do in the common order. The common order is, well, actually, the common order is starting with y, so dx will be the second integral. X boundaries are from 0 to 1. Y boundaries from 0 to 2. dy. Well, yes, it's all it's better to do it somewhere, not exactly in line. Not exactly in line, somewhere on the side. So from 0 to 2, x plus xy minus x squared minus y squared, integrated by dy. So y is the variable, and we pretend that x is a constant. So when we integrate x by dy, and pretend that x is a constant, what do we get? X, y. The problem is that, of course, it's very easy to get confused. Now, integration, differentiation, we have been integrating for 2 months, and then all of a sudden we started differentiating 2 variable functions again. Now we are back to integration. I know it's confusing. Sometimes you want to differentiate when you need to integrate the other way around. So, okay, to integrate, x is a constant, so we have to integrate by y, it becomes xy. Next, integrating by y,
Y squared divided by 2.
x, y squared divided by 2, x is a constant, so it stays there. X squared is again like a constant, so it's x squared y. And y squared, y cubed divided by 3. Between 0 and 2, but 0 and 2 only for y. So if y is 2, we leave x as it is. There's nothing about x, these are y values, so it's 2x. We put 2 instead of y. Next, we put 2 instead of y. We get 2x again. We put 2 instead of y, we get minus 2x squared. And we put 2 instead of y, we get 8/3. Now all these terms contain y, so if I multiply by 0, so I would need to subtract 0, so alright. I now can come back, we can return to our original integral from 0 to 1. So now 4x minus 2x squared plus 8 over 3 now integrated by x. Now that's a normal integral, a very basic integral. So what we have is 2x squared minus 2x cubed over 3 plus 8x over 3. Where? Here? Minus, yes, sorry, thank you. That's right. Minus. And minus. So that would be 2 minus 2/3 minus 8/3. 2 minus 10/3. 10/3 is 3 and 1/3, so it's minus 1 and 1/3. That's the integral. It's negative, okay, because this function obviously goes below the xy plane, so it has positive values, negative values, that's fine. We are not asked to find any volumes at the moment, only to perform the integration. So the process of integration itself is not going to be more difficult than this, at least for the Cartesian coordinates, because the function actually becomes very difficult, very fast. So if I make this integrand, the function, a little bit, tiny bit more complicated, then after the first integration, the result is horrible and very difficult to integrate. So the double integrals become complicated very fast. It's simply just because they are double. Because you do it once and you get something more complicated, and then you have to do it again.
But how about the polar?
Yeah, we'll deal with those as well. Those involve sines and cosines. So yes, trigonometric integration will be necessary sometimes. Sometimes. And 2D. 2D is double integral 2 region is bounded by, all right, let's have a look. Y equals square root of 6 minus x squared. What's that? What's that? What is y equals root of 6 minus x squared? Any ideas? What kind of curve?
Circle.
Yes, it will be a half circle. Notice that y squared is 6 minus x squared, so x squared plus y squared is 6. So the radius is going to be square root of 6, by the way. But it's a half circle, or a semicircle. Alright. So this is the square root of 6, this is the square root of 6, this is minus square root of 6. Y equals square root of x, simply square root of x, alright. Something like that. We know what the square root function looks like. So y is square root of x, and this is y is root of 6 minus x squared, or a circle. And anything else? Should be x equals 0, so it's the y-axis. Alright. So it's this top part, right? It's the top part. It's not the bottom part, because we need the region which is bounded by the circle, or rather by the half circle, by the parabola or the half parabola of the square root of x, and the vertical line x equals 0. So it's this is the region of integration. So now we may choose to integrate first by y, so we might choose to go first in the y direction vertically, and then we see we get from one curve to the other. Fine. If we go by x first, you see we have to change the function, we have to switch the functions halfway. That's not good. So let's go like this. The only thing we need to find is the upper boundary for x. You can, okay, trial and error, no problem with that. As we know there is one intersection point, you can do trial and error. Just try to... Any ideas what the value of x at that red point might be? We could just try and error. Could it be 1? Square root of 5, square root of 1? No. Could it be 2? Square root of 2 for this function, 6 minus 4 is 2, square root 2 for the other function. Okay, we guess x is 2 at this point. But I don't actually need you to solve quadratic equations or anything like that. Absolutely no need. What I do need is just to get this point, just to get this value somehow, even if it's just by a lucky guess. Because there's only one intersection point in this quadrant, only one intersection point. If we are lucky enough to guess it, and we know that there's no other, then it's fine. We have found it. Okay, so x from 0 to 2, y goes from 0, not from 0, but from square root of x to this, from square root of x to square root of 6 minus x squared, from the entrance point to the exit point, so from the lower curve to the upper curve. So we put simply these as the boundaries here, there. And the function is 2xy dy integrate by y first. So the rule, as you remember, was first we do the integral that we see clearly, and we see clearly this integral, so we do this first. Okay. I guessed.
Yes.
Yes. Well, okay, we can do it like this. 6 minus x squared square root must be equal to square root of x, the intersection point of these functions. 6 minus x squared is equal to x squared plus x minus 6 is 0, minus 3, 2 minus 3 is on the wrong side, so we have 2. Minus 3 doesn't work, by the way. You can't find the root of minus 3. So it's only 2. You can do it like this. Simply solving an equation, just like we do for normal integration, or you can just guess. As I said, it is acceptable to guess if you see that there are no many possibilities, that there's only one intersection point, and if you guess it, that's fine. If there are 2 or 3 and you guess one, you don't really know which one you have guessed. But if there's just one intersection point and you have guessed it, so it's formally, logically, it's correct and it's okay, even from the formal viewpoint. You guess the answer, you prove, or you can explain, or you can validate that it's the only one, then it's acceptable to guess. Okay. Right, let's do this integral first somewhere. X, 6 minus x squared, 2xy dy. So when we integrate this by y, xy squared from root of x to root of 6 minus x squared. Now, because it is the y value, and because y is squared here, we are in luck. The square root disappeared. So I have x times 6 minus x squared, that's y squared, this expression squared, minus x times this square, that will be simply x. So we see it's 6x minus x cubed minus x squared. And now we go back. Now we take this, and now we know that this is actually this expression, so now we put it back and integrate from 0 to 2, 6x minus x cubed minus x squared dx. And now a common integral. The most common of them all. 3x squared minus x to the 4th over 4 minus x cubed over 3. From 0 to 2. So it's 12 minus 16 over 4 is 4 minus 8 over 3. 8 minus
3 over
8 minus 2 and 2/3 is 5 and a third.
60.
Okay. So I don't think it's so bad. I do think that the worst part of this is correctly discovering the region of integration, describing it, figuring out the best order of integration, figuring out the boundaries of integration. Yes, finding this point. So that might be the difficult part, because the integrals, well, they can be bad, but I'm not going to give you bad integrals, bad functions to integrate. Alright, so now finally from number 4 something perhaps. But these are not interesting because basically in A the region of integration is a rectangle. In B the region of integration is a rectangle. In C, no, not a rectangle. And in D, x equals 2a, that's actually one line. I think, no, there's something missing, I'm not sure what exactly. Y is 0 and x is 2a.
What is A?
Something, some constant, but there's something missing. I have lost something. So D cannot be solved at this moment because there are not enough boundaries. There's one more curve missing, obviously. So we can do D. We can do C before we move on to polar coordinates. Or you can do it C. It's still simple. It's still simple. So for C, let's simply write the iterated integral, and then you can integrate it whenever you like. So x plus y is 1, x is 2, y is 0, y is 1. Let's sketch the region of integration before we can write the double integral in the iterated form. So y is 0, y is 1, those are vertical lines, horizontal lines. Y is 0 is the x-axis, y is 0. Y is 1, it's this line. X is 2, a vertical line. And finally, x plus y is 1 means y equals 1 minus x. So that's this, 1 minus x. If x is 1, then y is 0. If x is 0, then y is 1. It's this line. So this and this and this and this, these are the boundaries. So this must be the region D, a trapezoid. And now it's up to us to decide in which order to integrate. Again, or perhaps this time it's better to start by horizontal integration by x, because that will be from this to this. But if I start integrating by y, then this would be in here, in this part, it will be from this line to this line, and then all of a sudden it will be from the x-axis to this line. So we don't want two different integrals, we don't want a sum of two integrals, so it's much better to do it in a one. All in one, because the function is more difficult. So we would start integrating this time by x. So the integral by x would be from, that means that actually we need to write x as 1 minus y, because if I integrate by x, I have to express the x variable, don't tell me. I have to express the x variable by y. I have to express the x variable by y, so that's why I changed it. Because I'm integrating by x, I have to use the other variable for boundaries, so that my final expression will be in terms of y only. So it goes from 1 minus y to 2. The upper boundary, and then we have dy from 0 to 1, and the function 1 plus xy, 1 plus xy. So it will be just again a polynomial again. It will be a polynomial again. So I'm not going to finish this. You can finish it by yourselves. It's simple. This is not that one. Okay. Polar coordinates. Polar coordinates. Where are my polar coordinates? Okay. So what are those? Polar coordinates are used for practical purposes whenever we are, let's say, going in circles. We might use them in geography, sometimes in astronomy, definitely in navigation. So for practical purposes. And then there are many functions that look much nicer in polar coordinates than they look in Cartesian coordinates. The boundaries, the curves that bound our regions of integration often look nicer in polar coordinates. And so, how we do the polar coordinates? First of all, we have in Cartesian coordinates, when we have a plane, we have two variables, x and y. And every point can be defined by two coordinates, one of which is x and the other is y. In polar coordinates, it's slightly different. We still need only two numbers to determine the location of any point in the plane. But these numbers are defined differently. First of all, we have something, a path line, if you like, called the polar axis. We could write, okay, O, let it be L, doesn't matter. So we choose one direction and we draw basically a half line. We don't need a whole line. And then for each point, there are two coordinates. If I want to find the coordinates of this point, then I draw a radius vector, a position vector. I look at this angle, for example phi, and I look at this distance r. So the coordinates of the point A are defined by the two values. One of them is the angle and the other one is the distance. So we might say the phi and r. Usually the functions are defined as r in terms of phi. In other words, depending on the angle, we define the distance from the pole. This is called the pole. The pole, the center of the polar coordinates, and this is the polar axis. This is the polar axis. So generally, just like we have graph paper with squares for Cartesian coordinates, we can make graph paper for polar coordinates that would consist of, let's say, angles split in some decent intervals, for example, every 30 degrees, and then we have radius 1, radius 2, radius 3. So the system of polar coordinates might look something like this. For example, this point would have coordinates 60 degrees, that's pi over 3 and 3. If this is 1, 2, 3, the units on the polar axis. And this is the pole. Sometimes you can denote it by O or by B, it doesn't really matter what you call it. So if this is 30 degrees and this is 30 degrees, then the total angle is pi over 3, 60 degrees, and the distance from the pole is 3. So this is how we define polar coordinates, and now the big question is, how can we use them? We can't use them if we don't understand the connection between the normal Cartesian coordinates and the polar coordinates. So what we need is this connection. Let's suppose we have a point, point P with coordinates, Cartesian coordinates x, y. How do we find the polar coordinates? Or how do we, or maybe we can do it the other way around. We can express perhaps x and y using the polar coordinates. We need to be able to go both ways, but usually what we usually need is going from Cartesian to polar coordinates. Sometimes we need to go from polar to Cartesian simply to understand what that curve will look like. Okay, so this is x, this is y, this is r, the distance from the pole, if we put the pole in the same point where we have the Cartesian origin, and if we decide the polar axis to be, let's say, the positive x-axis. So obviously this then is the angle phi.
And it's arctangent y.
More or less.
Why?
Because if I'm here and I get the arctangent of this ratio, it will be the wrong one. You have to add pi or subtract pi from that, because arctangent, remember that arctangent values are only in the first and the fourth quadrant. So for the third, fourth quadrant, for the second and third quadrant points, we have to be very careful with those arctangents. And then again, that's the matter of convention. Do we say that phi can be limited from only allow the angle phi to be anything at all. If I allow phi to go outside this interval, it means I'm allowing it to circle the pole more than once. And that's actually useful for drawing spirals, for instance, and other curves which take circling the pole more than once. So it depends on the convention. So sometimes it's easier to deal with phi from 0 to 2 pi, and sometimes it's easier to deal with phi from minus pi to pi. So it's the matter of convenience, whichever way is more convenient. Different textbooks and different manuals of mathematics will give you different possibilities. All right. So first of all, we can see that obviously x is r times cosine phi and y is r times sine phi. That's from this right triangle. From the right triangle, the x value is r times cosine phi. The y value is r times sine phi, even when the angle is in the second or third or fourth quadrant, still produces the correct x and y values. So this is how we can go from polar coordinates to Cartesian coordinates, or actually we can go this way from Cartesian to polar coordinates as well. It's whichever way you like. So let's see what the Cartesian coordinates do backwards. R is obviously the hypotenuse, so we can use the distance in the plane, the distance from the origin or the magnitude of the vector. So the radius vector, the distance R is just this, the polar radius. Now, if we agree that we use arctangent, so then you can see, okay, it's time for you to get this, okay, take one and pass the rest on, take one, pass the rest on. I'll start from this end. Okay, 1, 2, 3. 1, 2, 3.
I'll do each one. Is that enough?
Okay? Anyone else? Not enough? Okay, let's go over the circle here. Okay. Alright. So what we see is, I simply don't want to write the basics, too much of basics on the board. That's why I just decided to give you the paper. So yes, if x is positive, then we can say that it's the arctangent. So in the right half plane, for positive values of x, the arctangent works perfectly because arctangent values are from minus pi half to pi half, and it will give you the correct values. If we have x negative, then again depending on how we choose to take the polar angle, it depends. So obviously, if we have the third quadrant, then we could take arctangent plus phi. If we have the second quadrant, if we have the third quadrant where both coordinates are negative, then we could take the arctangent minus phi or arctangent plus phi. It depends on which kind of phi limitations you choose.
Sorry.
Yes?
What is correct to use? In which order is it correct to use R phi or phi R? The coordinate domain.
It depends. So in many textbooks you write R phi r first and phi second, but actually when we define functions, it's usually r is defined in terms of phi. So generally, usually, r is the dependent variable and phi is the independent variable. But I have seen very often that they write r, phi in that other order. It will be, usually it will be quite obvious which order we should use. So r phi or phi r, yes, generally it would be r phi, but if we want to look at functions and the relations between these two variables, usually the angle is the independent one, and the r coordinate is the dependent on phi. Alright, now the double integral. Now the double integral. How can we convert the Cartesian integral to a polar double integral? Okay. What we do is, suppose we have the double integral on some region f, x, y, dx, dy, without the iterated form, simply the double integral form. What we do is, of course, we perform this transformation, and of course we get a different function. So this function becomes some other expression in terms of r and phi. If we write, instead of x in this function, we might write r cosine phi. Instead of y in that function, we write r sine phi. We get some other expression in terms of r and phi. That's why I'm changing the name of the function to the capital F. That's one thing. Now, we are still using the same region of integration D, but I'm putting a little star there simply because it will be described not by Cartesian curves, not in terms of x and y, but the functions describing this region will be in polar terms, in polar coordinates. So that's why I'm putting this star. It's still the same region, but it will be described differently in terms of polar coordinates. And now to transform this, dx dy is now transformed, interestingly enough. So if I say dx dy is a basic tiny square, dx dy and the area, now in the polar coordinates it becomes something like this, the basic thingy. The basic element of the area in polar coordinates is like this. And there's this interesting thing.
And the angle is 1?
What one?
The angle.
The angle?
In polar.
In this?
Yeah.
No, that's the thing. The angle, this angle is d phi, delta phi.
Okay.
The change of the angle.
It's really small.
The change of the angle, very, very small. So yes, it actually approaches 0. This is dr, or delta r. So again approaches 0. So basically it becomes a very, very tiny piece of the plane like this. But we can't write d phi dr because r is the dimension, the length. But phi is just an angle, no length involved there. But of course, if you remember that the length of the arc, basic trigonometry, geometry from school, the length of an arc can be expressed as phi times r, using radial measure in radians. So basically, if I take a small change of phi, the length of this arc, actually will be d phi times r. D phi is the angle and r is the radius of the arc. So the length of this little tiny arc is not just d phi because that's not length, that's an angle, but r times d phi. That means that this product, dx dy, instead of this product, we have to write r d phi dr. So there's an extra r. An extra r appears in the integrand. And that's important. Because if you lose this, everything goes wrong. You have to be very careful. It's not simply d phi dr, but to make this some unit, some tiny element of area, this has to be expressed as length. So we can, of course we can pretend it's still a tiny little square, because when these become tiny, 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 it's more like, almost like a square. We can pretend that it is at least. But in order to do that, we need to understand the length of the side, which is the length of arc. Angle in radians, that radius, that's the length of arc. Geometry from school. Okay, so an extra r appears. So when we have changed the function, that's simply done because it's pure algebra, you simply insert these. Then the difficult part usually is changing the boundaries of this integral of the region into the polar form. So the problem is expressing the boundaries of the region in polar form as polar functions. And that's the fun part. I would say this fun. So in the first example, we have x squared plus y squared equals 16, that's a circle. So that's the region of integration. In the Cartesian coordinates, it looks like this, and the radius is 4. In the polar coordinates, it's very simple actually. We can say that for any angle, wherever we go, the r value is the same. The distance from the center is the same for all points of this circle. So for all values of phi, this curve is simply defined by r equals 4. And you see how it is easier to describe a circle in polar coordinates. You simply state r equals 4 for any phi. And this seems very clumsy in comparison to this. Or, of course, we can use algebra. I could write r squared cosine squared phi plus r squared sine squared phi equals 16. R squared cosine squared phi plus sine squared phi equals 16. What's this? 1. So r squared is 16 and r has to be positive, so it's 4. Although sometimes we need r to be negative. Not here, not for our purposes, but when working with polar coordinates, what would that mean? R is negative. Goes the opposite way. Sometimes actually it happens. You can play with some graphic software. If you can make it do, if you can make it do things slowly, and it draws beautiful flowers, for example, like this. All you have to do is find the correct equation and to enter. So, alright, so we now can see that this domain can be simply described as r equals 4 for all values of phi. That's my first example, and I'm now going to try to do this. So, double integral dx dy, square root 25 minus x squared minus y squared. The region D is this. So now, obviously the region D, we have solved the region D. We know that it's a circle and it can be described by the boundary of the circle. Can be described by r is 4. For the circle itself, of course, r is from 0 to 4. Anything from 0 to 4 for all angles. Now let's change the function. So the function we have in terms of x and y, the function is 1 over square root of 25 minus x squared y minus y squared. Now, what's this? How do we change this function? What becomes of this function?
X squared.
So this actually becomes square root of 25 minus r squared, because we know that x squared plus y squared is r squared for any point. So it becomes this. It becomes this. Actually, we know how to integrate things like this. Arcsine. So that's the function. So this is the function now. This is what the function is in terms of r and phi, and we can see that this is simply for all values of phi. Obviously, phi does not influence the value of the function, only the r value does. So here we have two variables. Very fortunately, in the new form, we only have one variable. That's useful. That makes things simpler. And now we have to change this integral now. So the new description, the function 1 over square root 25 minus r squared. Now to change the differentials dx dy, we have to exchange it by r d phi dr. Don't forget this r, this extra r. So in the end, we can say it will not be our tangent after all, our sine after all, because this is, r is the derivative of r squared, well, more or less, approximately. So now, how do we write this as an iterated integral? Obviously, there will be this function r over square root of 25 minus r squared. Obviously, it would be nicer to integrate it by r, because the function is in terms of pure r. So it's, of course, it's easier to integrate by r, and in polar coordinates, these double integrals are usually taken first by r and only then by phi. First by r. So r, the boundaries of r, what are the boundaries of r? Anything from 0r to 4, from 0 to 4. For any angle, we integrate along this segment from 0 to 4. So r can change from 0 to 4 for this integral. And then we go the full circle for y. So we can write from 0 to 2 pi. The angle changes from 0 to 2 pi, full circle. Radius changes from 0 to 4. We will not generally consider negative r values for our purposes. It's not necessary. And now all we have to do is integrate. Perform the integration. This. Nope. Nope. Okay, 0, 4, r dr square root 25 minus r squared.
It's r.
No.
Yes.
Okay. Substitution.
Yeah.
Okay, let's suppose 25 minus r squared is u. In that case, du is minus 2r dr. So to change to the new variable, yes, the methods of integration still work. Minus 2 here, in front of course, minus half then. Now I can rewrite this. Now I can rewrite this as minus 1/2 integral from 0 to 4. Well, actually, because I need values, I will only need an nth number. So obviously, if r is 0, then u is 25. If r is 4, then u is 9. Right? So actually, I'm going to change to the variable u completely. So if r is 0, u is 25, so the lower boundary will be 25. If r is 4, then u is 9, so the upper boundary for u will be now 9. And I simply completely switch over to the new variable u. I will not return back to r. No need. So I have du divided by square root of u, which is the power minus 1/2. So what we have is u to the power minus 1/2 du here. Integrated. Okay, now raise this part while you think about the integral. So it will be when integrated, it will be u to the power add 1. So u to the power 1/2 divided by 1/2. So this will be actually 2 square roots of u, but then we still have this minus half in front. Minus 1/2 times this, so that will be minus 1, right? 25, 9. So it's minus square root of u from the values 25 and 9, between the values 25 and 9. Or I can write square root of u from 9 to 25 after all. So that would be 5 minus 3, it's 2. It's just 2. It's just 2. It looks, well, it might look, I don't know. Because after reading all your tests, I'm really confused which of you actually do remember things and which of you fumble and copy. Okay, so this integral turned out to have the value 2. So I integrate 2 d5 from 0 to 2 pi. When I integrate that constant, it becomes 2 times 5. So this becomes 2 phi between 0 and 2 pi. Which means it's 4 pi is the answer. 4 pi is the answer. Just like that. So yes, if you don't remember your methods of integration, it might hinder you a little bit. Or a lot. Okay. Now the next one.
Is it a square unit or
No, it's simply something. Because we don't know what the function is. We don't know what the function is. If we want to find for example, the volume below the shape described by that function, then yes, that would be cubic units, by the way. But because we don't know what that function signifies after all, there's no need for any units. Next example is integrate x squared plus y squared dx dy. The region is given, actually shown by x squared plus y squared equals 2y. Now we have to figure out what it looks like. First of all, we need to know what it looks like, and we need to know how to convert it into polar coordinates. We need both. It's not enough that we simply replace these by r sine phi, r cosine phi. We still need to know what it looks like, because otherwise we will not be able to arrange the integration correctly. And then x is 0 and y is x. Alright, so this would be a circle if instead of 2y I had some square. I don't have a square. So what I'm going to do is I will find the actual center of this square. So a little bit of rearranging things. X squared plus y squared minus perfect square then. So I have to add 1 to the other side as well. And now I have x squared plus y minus 1 squared equals 1 squared. Now I have a circle with the center at 0, 1. And the radius is 1. Remember, x minus x0 squared plus y minus y0 squared equals r squared is a circle with the center at the point x0, y0. So sometimes we need to rearrange that equation a little bit to figure out what the center actually is. The center is not at the origin, the center is somewhere else. So I move this 2y over to the left side and see that to finish the square, to complete the square, to get the perfect square, I need to add 1. And then of course I have to add 1 to the other side to keep the balance. So now what it looks like is the center is at 0, 1. The radius is 1. So the circle passes through the origin and through the point 2 on y-axis. And of course here we have the point minus 1, 1 and minus 1, 1, so the circle would look like this. So the circle would look like this. I had to do this so that I can actually find the location of the center and the radius of the circle so that I can actually understand what the circle looks like. Because we are basically used to Cartesian coordinates. If, I don't know, if we had started at school with polar coordinates only, perhaps there are some aliens, Martians, on their own planet who start with polar coordinates and they have difficulties understanding Cartesian coordinates, who knows? Now this other line, y equals x, oh, it passes through 1, 1, so it passes through this point. This point is 1, 1. This line. And if I want to see the region bounded by this circle, this line, and x is 0, that's the y-axis, that would be this region, like this. It's this region. And now how do we integrate in polar coordinates? First of all, of course, we need to describe this in polar coordinates, but basically we see that for all angles from this to this, we have to figure out what those angles are, what the boundaries are. The integration will go r from 0 to the circle. So we need the equation for the circle. Alright, so let's do it. R squared cosine squared phi plus, oh, this is actually r squared. No need to bother. So this is actually r squared, and this is 2r sine phi. Divide both sides by r equals 2 sine phi. That's a good equation because it expresses r in terms of phi only. So this means that if I integrate first by r, it means the r values will go from 0 to 2 sine phi, because my direction of integration will be like this. From this to this, from this to this, from this to this, from this to this, like that. And then, yes, d phi. How will we change d phi? Which is the minimal angle? The smallest one?
45.
45 degrees, that's pi over 4. And the maximum angle we reach is pi half. Like this. Now, what else we have? Oh, we have this function. That's r squared. But when we change to the coordinates, d phi, dr, we need an extra r. So it's r squared times another r. Altogether it will be r cubed. So altogether we have r cubed to integrate. But this is easy. So to to integrate this, it will be r to the 4th over 4 between 0 and 2 sine phi, and then I will integrate it by d phi, pi over 4, pi over 2. Now, what I'm doing is I'm not integrating on the side because it's such a simple thing to integrate. I can do it here. I don't have to do it somewhere else. It's not that confusing.
Why do you want more R?
Where?
R cube?
R cube? Because we transform dx, dy to r, d phi, dr.
Fine.
That was this thing.
Yeah.
There's this extra r thing. When we change to polar coordinates, we always see an extra r. There's always an extra r.
But where did you get another r? So 1r is from x squared plus y squared? And
No, it's r squared.
um,
It's r squared. This is r squared. This itself, this by itself is r squared. So what we have is from pi over 4 to pi over 2, we have, okay, 2 to the 4th is 16 divided by 4 is just 4, and then we have sine to the 4th of phi d phi. Okay. The 4th power of sine, we have to use, as you see, I have shown how to do it. We have to use formulas for decreasing the power, decreasing the exponent. So I'm not going to do this on the board, but remember that we had some formulas, and this is the old one. And one of those was, if I have sine squared of any angle, I can write it as 1 minus cosine of double angle divided by 2. So actually, if I have 2 sine phi, it equals 1 minus cosine 2 phi. Like this. And because I have 4 sine squared, phi to the 4th, then this obviously becomes 1 minus cosine 2 phi squared in there. And then I have to open the brackets and do it once again, something similar to this. So remember that sine square of any angle can be expressed like this, getting rid of a square, decreasing the power. And the cosine square of any angle equals 1 plus cosine of the double angle, phi over 2. If you ever see cosine square, you can change it to this in order to be able to integrate, so that we can integrate. And now, of course, I would still have a square, so I would still need, for this, I would still need to apply that formula. And that's trigonometry. While I understand that many of you won't ever need trigonometry in business, economics, and so on, the rest of you will. So you should look up those formulas, make a point to print them out or copy them into your notebooks or somewhere, because they are useful for integration, as we already saw when we integrated, when we looked at the methods of integration. So these two formulas, which help us to go from the square of sine or cosine to the first power, first degree. Simply to decrease the exponent. Because we don't really know how to integrate a square or a 4th power. We know how to integrate sine or cosine of something, but we don't know how to integrate sine squared directly. So we have to do this.
So how does the 2 sine phi come from? I know it's r equal to 2 sine phi, but why is from 0 to 2 sine phi, not from 0 to 2?
Because this, okay, this is actually, this describes, this is the equation of the boundary line of the circle. So the value of r, if we want to go through the whole region, r can start at 0, the least value of r is 0, and then when we increase r, how far can we go? Only to this line, only to this curve. And that's why we use the equation of that curve as the endpoint, as the stopper, if you like.
But then, isn't it 2? Oh, no.
It's this.
Okay, it is.
From 0 to this curve, and the curve is described by this equation. And then for each of these segments, we simply look at this angle, at this angle, at this angle, for all angles from pi over 4 to pi over 2. So, as I said, it takes a little bit of change in thinking. You have to switch something in your mind to understand that we do the same thing, but slightly differently. We are not going horizontally, vertically, but we are going outwards and then like a fan by an angle. Okay, what else do we have? We have exercises. So it's important to be able to understand how these integrals are composed. What are the angles acceptable? And what are the r values acceptable? I'm not sure. We have 5 minutes. Is there anything we should do?
What is the solution for this? I mean,
For this?
yes.
Okay, I'll finish it. So now I have this integral. So now it becomes pi over 4 pi half. Now this becomes 1 minus cosine of 2 phi squared from those formulas of sine square. I got this. I still have a square there, so I have 1 minus 2 cosine of 2 phi. I can integrate 1. I can integrate this. And then I have cosine square, which I cannot really integrate directly. So I have to do this again. So remember, I just had it on the board. Cosine squared of any angle is 1 plus cosine of the corresponding double angle over 2. So now this will become 4 phi from the formula. This. 1 minus 2 cosine of 2 phi. I will integrate this. Plus now this, using this formula, this will be 4 phi because instead of alpha I have 2 phi. So it's 1 plus cosine of 4 phi over 2 d phi. Now these are all possible to integrate. These are all possible to integrate. I can go this way now. Quite amazed, going up, down, and so on and so on. So for this I have from, okay, I can actually start by integrating already because there's nothing more. I can already integrate. So this is 1, and then there's 1/2. So it's 3 halves. So I can write it 3 phi over 2. These are integrated now. Now I'm integrating minus 2 cosine 2 phi. So the integral of cosine, the primitive function of cosine is sine. So it's 2 sine of 2 phi. Integrating, remember we have to divide by k, the coefficient of the inner linear function. Divide by 2 because it's 2 here. That's integrated already. Plus, now we have to integrate cosine 4 phi divided by 2. The integral of cosine is, as always, sine. So it's sine of 4 phi. We have division by 2 naturally, and we still have to divide by 4 because of this. Remember that we always have to divide by that coefficient.
You cannot take outside the 1 half.
We can, but over 8. I already subtracted for this term, I subtracted both the boundaries already. Minus, now, sine of 2 pi means sine of pi, which is 0. Sine of pi is 0, and sine of pi half is 1. So it's 0 minus 1. And for the third term, so I'm doing each term separately. I'm not doing all these for pi half and then minus all these for pi fourth. I'm doing subtraction, both boundaries for the first term, minus subtraction for both boundaries for the second term, and now finally the third term, which is sine of 4 pi over 8. That's the nicest one, because 4 times pi half is 2 pi, sine of 2 pi, 0. 4 times pi fourth is pi, sine of pi, 0. So this is the best part. So we see that the result is 3 pi over 8 plus 1. That's the answer. That's all.
The integral part is the hardest. Integration.
What integration? Well, which integration? We don't have to do any more integration.
No, I mean this integration is hardest.
This one? Yes, it is. That's, again, yes, it takes getting used and remembering and let's say, putting in an obvious place these two formulas for sine square and cosine square so that you can apply them, because they are necessary for integration. They are some of the most necessary things for integration. Whenever you do trigonometric functions, you might need these. If the power is odd, it might not be so bad, because you can change it into the other function. But if the power is even, you can't escape this. You need to use them. Okay, once again, I really apologize because I honestly printed out everything I needed.